Let me try.
So there'll be some limits that may be on the
Screws is gonna take
calculator
your
part
battery out.
that you cannot do anything algebraically, or you can't do anything with your identities to figure out. So here's an example. Limit as x goes to 0, the bottom is definitely 0, the top is definitely 0. This is the indeterminate form. So how do we use our calculator to do this? First thing you're going to do is type it into your calculator.
I think we're getting close.
Secondly, we're going to set up our table, and I'm going to actually show you some tricks in here. So let's go to our calculator, slide this over here so you can see it.
Tips and tricks.
Whoa, there we go.
What's happening?
Okay, so I'm going to go to y equals, and I'm going to use my fraction button, and it was 10x over 3x, so 10x, close the bracket, over 3x. Perfect. Now in your table of values, so if I go second table, I see a table of values, and probably yours looks like this when you go to it right away. True? Does it go 0, 1, 2, 3? Maybe? Okay. Lots of people have it set to go up by ones. You can change what it goes up by, because we're curious, does it get close to something as it gets close to 0? But at -1 and 1, we're not really close to 0 yet. So two things you can do. You can either go to table setup, which is above the window button here. So I go second table setup, and I can change it. Right, I'm going to go to 0. I'm going to start at 0 and change it to go by 0.01s. That's really smaller now. Now when I go to second table and I can scroll up, I get an idea that I'm getting closer to something. It's got 0.333, 0.333. So one way you can change it is by going to table set. The other way you can change it is just by hitting your plus button. So if I go +1, it changes things back to +1. If I go plus 0.001, it's a lot quicker, I find. It changes it to going up by that. So it's kind of nice that you can use that plus key to change what it's going by. It sure looks like it's going to 0.3 repeated. So after I've got my table of value and I see that, I make this assumption that based on my graphing calculator, it's getting closer and closer to 1/3. If we look at it and actually hit the graph button, we sort of say, hey, it looks like it's going to something there. At x equals 0, it sure looks like it's connected with a hole in it. Rather than sometimes the graph goes like at, if it was the limit as x goes to, what is this value here? Maybe it's 1. I don't know what my scale is. That would tell me I don't know at that value.
Pretty laggy, bro.
It's probably pi over 2 at that value. Question?
Not same as
Are you in radians or degrees? Yeah. And then here, it's probably because of the size that you got here. So if we go zoom 6 to standard window, okay. If we go zoom, it's 30. Maybe I go zoom.
Or what are we talking about right now?
Number 7. It's a little bit.
Don't trust pirates.
That is very, yeah, it is kind of. You don't like those grids?
Oh, crap. You didn't come to my birthday parties back in the day.
Questionable things.
I may just also look at your
Kago saw me like one time joke. It's in grade 5.
Bro, that's the method. I'm telling you. Yes, bro.
I'll just do an interview with someone that is
One time jokes. Now you're out.
Not anymore. Bro, this is a silly ass graph, bro.
I'm both of them.
Okay. So we look at our next one.
This top 10 silly graphs.
Cos 5x minus 1 over x.
I like this one.
So we go to y equals cos, wow, y equals cos 5x minus 1 over x. Now, if you want to see the graph, sometimes zooming to number 7 for zooming to trig is a nice one. I'm kind of feeling in this one, as x approaches 0, does it continue and get really close to 0, or does this have a jump discontinuity? I'm a little bit unsure just from my graph. So then I'm going to go to my table, and I'm going to look at my values as I get close to 0. And maybe I even hit the plus sign and make my jumps even smaller. You know what this e to the minus 5 means? That's scientific notation times 10 to the negative 5, right?
Yeah.
It makes me feel like both sides are getting really, really close to 0. So again, on this one, I'm feeling like this is really, really close to 0, even though in my graph I see that jump. Later on, we're going to learn a technique that's going to make these really, really easy to do. It's called L'Hopital's rule. Named after a mathematician that stole it from another mathematician, is now famous and has his name connected to it for all time, even though he did nothing but buy the rights to it. Never figured it out himself. Kind of cool. Right? We'll talk about that history when we get there. It's kind of interesting history. But we'll find a way to do this later on that makes it a lot easier. But right now we have our graphing calculator. Here's our next one, sine squared 2x over x squared. So again, I would go to my calculator. If you want to do sine squared on your calculator, you're going to have to go brackets first, then write sine, bracket 2x, bracket, bracket. Do I have, oh, it made it, okay, bracket, sine, which automatically made a bracket, so I don't need another one, 2x, close that bracket, close that whole thing, then make the whole thing squared. We can't put the little squared in between on your graphing calculator in the same way. So that would be sine squared 2x, all divided by x squared. So on the bottom, I'll make that squared. I'm going to look at my graph. It sure looks like it's getting close to like 4 or something. But I don't know exactly, so I go to my table. And I was already at 0.001. I'm feeling close to 4. So we put our table in. Yeah, if we did 0.01, it's like 3.99, a little bit closer. But I guess at 0.01, it was already so close. So this gets close to 4. Okay? And what you have in your back of your head is that mathematicians were figuring this out hundreds of years ago without graphing calculators. So how did they do it? We're going to develop those techniques. Okay?
I think we had secret calculators.
They had secret calculators. Yeah. Okay. And then this is going to help you a little bit with some of the questions on your take-home quiz. I think there's a couple with absolute values. Maybe you saw them already. How do we deal with absolute values in a question? So here I have the limit as x goes to 3 of x minus 3 over x minus 3, which would make us think that maybe it's equal to 1, because can those both cancel out? But the absolute value causes a little bit of problems. So let's look at the limit from both sides. If I went from 3 from the left side, do you see that the top is always positive? So it's going to get to a very small positive number divided by a very small negative number. And technically, that's going to look like -1. Because there'll be the same number on the top and the same number on the bottom. They cancel out, but one's positive, one's negative. If I look at it from the positive side, they'll both be positive numbers, because the absolute value is always positive. But now as I'm going from the right side, that's what this 3 plus means. I'll have the same small positive number on the bottom, which will equal +1. So when we go to this limit, we could say the limit does not exist. Absolute value functions can sometimes be easier understood as a piecewise function. So if I had just the top, if I just look at f of x equals the absolute value of x minus 3, I could rewrite this as two different pieces. Like, if the inside is positive, the absolute values don't matter, right? When is the inside positive? When x is bigger than or equal to what number? 3. So this graph is going to equal x minus 3 when x is bigger than or equal to 3. But when x is less than 3, do you see that that would always be negative? What does the absolute value do to negative numbers? It makes them positive. How do we write that mathematically? You could just take whatever the answer is, which is x minus 3, and put a negative in front, because it's negative, that would make it positive. And now we've rewritten this as a piecewise function. Now look at the question that we were dealing with. We are dealing with the limit as x goes to 3 of absolute value of x minus 3 over x minus 3. I'm going to let g of x equal this, and I'm going to rewrite g of x as a piecewise function, which means I'm going to take this x minus 3 and say, when x is bigger than or equal to 3, this is just x minus 3 over x minus 3. Right? And when g of x is less than 3, when x is less than 3, then the top, I'd have to put a negative out in front to make it positive over x minus 3. If I write it as a piecewise function, I actually can simplify this, right? Because this over this is just 1. And this over this, they would cancel out, and that would be just -1. And as a piecewise function, from the left, it's always going to be -1. From the right, it's always going to be +1. So we can tell that this does not exist based on that. So rewriting something, an absolute value, as a piecewise function can be very, very helpful. So two ways of thinking about this. You can either think about coming from the left and coming from the right and seeing what you get, or you could write it as piecewise functions and actually simplify it and see what you get. So if I come from the left, this can be broken up to be limit as x goes to 4 from the minus side of x times by the limit as x goes to 4 minus of this. And this will be a small negative number divided by a small positive number. And this would just be 4, right? If you're going close to 4 of x, you're going to get close to 4. So from the left side, this becomes 4 with a negative. If we go from the right side, again, I can break it up. Limit as x goes to 4 of x, and limit as x goes to 4 of x minus 4 over this. This will be positive number over positive number, which is 1. And that's still 4. 4 times 1, this is 4. So based on the negative side and the positive side, we could say that the overall limit wouldn't exist. We look at its graph, it's broken up that way. Do you know how to put the absolute value into your graphing calculator? I'll show you everybody who doesn't know. So if I pull up the calculator here, I go to y equals, and we had x times by alpha equals the fraction, whoops, there, x times by absolute value was on the, oh no, it wasn't x times, it was x after I factored it out, but whatever. X minus 4 on the top. And the absolute value you can find by hitting the math button, going over to number and ABS, push that. You can find it that way. And when we hit graph, if I go zoom 6 to standard graph, we see that break in that graph. How would we write this as a piecewise function? Okay. Where does the absolute value change from positive to negative? At 4. So I'm going to look at values bigger than or equal to 4 and values less than 4 to break it up as a piecewise function. When x is bigger than or equal to 4, the top, if I factored it, would be x times x minus 4. Divided by, and the absolute value when x is bigger than 4 is positive, so it would just be no need for those absolute value signs, it would just be x minus 4. And maybe you can see that it's just x in those situations. But when I look when x is less than 4, my top factored out would still be x times x minus 4. But the bottom, x minus 4, would always be negative. And the absolute value would make it positive, so I can show that by putting a negative out in front of it. And maybe you see here, these would simplify, and you're left with x, and the bottom one would be negative x. And the limit as x goes to 4 would be, left side would be on the bottom one, right side would be on the top one. They don't go to the same number, and we have a problem. So the limit as x goes to 4 does not exist. So anytime you have piecewise functions, it is helpful to look at the left side and the right side and see what you get. Some questions there? Now previously, we had the very informal definition of continuity that I gave you, where it was like, hey, you draw that part of the graph and you don't lift your pen, which I really like as a visual, it's really easy to understand as a visual. Officially, something is continuous at a specific point if the following three things happen. Okay? Something is continuous. First of all, the point has to exist. If that point is undefined, it can't be continuous there because you definitely couldn't draw through it without drawing that point. So step one in continuity at a specific point is that point has to exist. Then the limit has to exist. So coming from the left and coming from the right has to go to the same thing. But these two alone doesn't show something's continuous. Because if I could have this, right? F of C exists. There we go. Here's C. I've got the point. And if the limit exists, I could have that. Is this continuous? No, because it has a jump. Right? If I was drawing this with my pencil or pen, I would have to go here and I have to lift my pen, fill in that dot, then start again and go here. I can't draw this whole thing without lifting my dot. Step 1 and 2 is not enough to say that something is continuous. Step 3, well, the limit exists and this point right here actually has to be right in there. Then everything is good. So those three things make something continuous at a point C. Right? If you can draw through the point C without lifting your pencil, that's the informal definition. The formal definition says that point has to exist. Because if you're going to draw it, it has to be there. And as you're getting close to the point from the left side, you have to be getting close to it. And as you're getting close to the point from the right side, you have to be getting close to that point. Then we would say the graph is continuous at the point. Okay? This graph, obviously you draw through it. Okay? Most of the time, you are going to use your informal definition to say, hey, it's continuous. But if a question asks for more formality, you would have to say, yes, I know the point exists. I know that my limit exists, and my limit is equal to the point, therefore I'm all good. So often, 2 and 3 kind of, you sort of combine them. If you know the limit exists and it equals the point, you've done 2 and 3 at the same time. Okay. This one has a hole, so it doesn't exist at the point. This would not be continuous at A. This one definitely jumps. Okay? It doesn't exist. F of A exists, so part 1 was good, but the limit doesn't come to the same thing. This one doesn't have a limit. This second one here, like, check, check, check. Step 1 is good, step 2 of continuity is good, step 3 of continuity is good. The second one, 1 is bad, 2 was good, 3 was bad. Right? The point doesn't exist at A. So you already know 1 is bad, but 2 would be good, 3 would be good. Okay? This one, the point exists, good. Does the limit exist? No, that's bad. The limit doesn't exist, so the third thing would be bad. Okay? The last one, 1 is good. 2, the limit exists, is good. 3 is bad. Because the limit exists, the limit would be 1, 2, 3, 4, 5-ish, 4.5-ish, right? But the actual value of the point is just under 3. So you will get questions that will ask you, right, if there's a long answer question, is this continuous at x equals 3? Sometimes your gut will be just like, yes, it is. Okay, that's not enough work on a test. You have to show all 3. You have to show, yes, the point exists, yes, the limit exists, and yes, the limit and the point are the same number. Therefore, it is continuous at that point. which is going to bother you a little bit because determine if this is continuous at x equals 1. The answer is yes. I know that I can draw that parabola without lifting my pen. It's continuous at every single point. Every polynomial function is continuous at every single point because there's no non-permissible values of x. But that's not enough. We have to go through the 3 steps. So step 1. Can you plug in 1? Yes, it's equal to 5. Does the limit exist? Yes, because it's a plug-in one. You can just plug it in. And then we have to make a statement that, yes, the limit equals the value. Therefore, it is continuous. And of course, you can draw a parabola without lifting your pen. But this was an interesting thing historically in calculus. Because historically in calculus, for the longest time, people were like, you just know. But someone was like, we need to make this formal. And once they made it formal with these 3 things, then it opened up like, oh, now we can solve these problems that were causing us issues before because we weren't formal enough. So the formalization of this allows to solve more complicated questions, even though in a lot of situations, you're just going to be able to look at something and say, I know it's continuous. I know I can draw that without lifting my pen. And almost all the graphs you've dealt with in your entire life up till now have been either completely continuous or mostly continuous, except for like 1 point. Right? Non-permissible values that have asymptotes. When you drew those graphs, they were continuous everywhere else except for your non-permissible value. But everywhere else you could draw that section without lifting your pen. But then, yeah, like then mathematicians, like there are some crazy things that people have come up with and say, hey, what do we do in this situation? Oh, now I want to look up something. Okay, but I won't. Not right now. Is this continuous at x equals -2? So step 1, can you plug in? Can you plug in -2? No. So it doesn't exist. So we can right away say it is discontinuous. And maybe I even add here at x equals -2. When you graph these in grade 12, what happened at -2? Is it a hole or is it an asymptote? That one will be an asymptote. So graphically, we can see, and you just have to show that one of the 3 things doesn't work. You don't have to show they all don't work. As soon as you find one doesn't work, you're done. It's discontinuous. So which one did we find here? We found out that 1 didn't work. If you did the limit, it doesn't work. Well, obviously, since the limit doesn't exist and the value doesn't exist, are they technically equal because they're both DNE? Does not exist? I don't know. No. I think we'd have to say they're technically, just because 2 things don't exist doesn't mean they're equal. Right? Santa Claus and unicorns aren't the same thing. They both don't exist. I'm sorry. I might have. I'll have to put this for adults only video as a result. We don't want to ruin things for small children. That would be quite something. Well, I learned that Santa Claus didn't exist in grade 5 because my friends told me, and I finally asked my parents. There we go, right? Is there some kid out there like, oh, I learned that Santa Claus didn't exist when I was learning limits? That would be quite something. Ooh. They like to ask you continuity questions at piecewise functions. Is it continuous at x equals -1? Does it exist at -1? Yeah, the middle one. The middle one says yes, it exists. So step one, we can put a little check mark. Step one is good for continuity. What about the limit? If we look from the left side, the limit is -2. If we look from the right side, the limit is -2. Therefore, the limit exists. And step 2 is good for continuity. The limit exists. It's equal to -2 from the left side and the right side. Is the limit and the value the same? No. We fail at step 3. It is not continuous at that point. So you need all 3 things to come up and be true for the limit to exist. Okay. This is a fun multiple choice thing that they do. They say, here's a piecewise function. And it's continuous. What's A? What's B? And it's continuous everywhere. Where do you think the problems might occur on this one? First of all, 2. Straight line of 2. Can you draw that without lifting your pen? Yeah. I'm not worried about anything on that one, except for when I get to -1, because -1, it jumps from this equation to this equation. And then here it's always -2. So that seems fine and continuous. In the middle, ax plus b, that's a line. We need it to be continuous everywhere. If we think about this graphically, whenever x is less than or equal to -1, it's equal to 2. So I can put a solid dot there, straight line there. Agree with that part? And whenever x is bigger than or equal to 3, it's -2. So 1, 2, 3, I can put a dot there because it's equal to, and that's always this. The ax plus b, if I'm going to draw that in so that it's continuous, does it make sense that the open circle here would have to be right there and the open circle here would have to be right there? It'd have to go like that and join them perfectly. Based on that information, can we find out what A and B are? I'm pretty sure A is going to be negative. Sure looks like it has a negative slope. If I drew it nicely, it looks like B might be 1. But I don't know if I drew it nicely enough. I kind of didn't use a ruler. How do we go about figuring this out? Okay. So again, the first thing we discovered, the only values where things could be discontinuous are at x equals -1 and x equals 3. Couple of ways we can go about solving this. If x is equal to -1, okay, then the ax plus b has to equal 2, right? If you plugged in -1, if that hole was right at the right spot, you would need it equal to 2. You could plug in -1 for x, and you get the equation that 2 is equal to -a plus b. If x equals 3, then we need the ax plus b to equal -2. Which if you plugged in 3, you'd have 3a plus b equals -2. What did we just make? A system of equations. You will never directly be asked to solve a systems of equations in AP Calculus, but many, many, many times it'll just sort of appear in the middle of a question. So how do you solve a system of equations? Well, you can either use substitution or elimination. There's my two equations. If I add these together, or if I subtract them, sorry, my b's would go away, right? I'm using elimination. 2 minus -2 is 4. -a minus 3a would be -4a, and b minus b would eliminate. Or you could use substitution. You could get one of the letters by itself and substitute it to the other one. Either way, you're going to find a is -1 and b is 1. Okay? Just looking at this question, the sign part of mathematics, as mathematics gets more complicated, is the number of correct methods to something goes up, which is nice in one way. Oh, you mean I can think of this in different ways and figure it out? Which is really nice. Not nice for if you're like, I wish there was only one way I could do this and do that all the time and get it right. Because a lot of us like that. Like, this is the way that I do it, regimented, follow the steps, okay? As I was doing this method, I was like, ooh, I thought of another method. Couldn't I just, if I wanted to find this one, couldn't I just take this point, -1, 2, and say that's on my purple line, and take this point, 3, -2, and say that has to be on my line. And then, what's my slope? Well, this has a rise of 1, 2, 3, 4, and it's going down, and it has a run of 1, 2, 3, 4. My slope is -1. And if I did y equals mx plus b, and I know my slope is -1, I could choose either of these points and plug it in. So I could plug in -1 for x and 2 for y. And no, -1 for x and 2 for y. Yes. Yeah, this is good. And this will be +1. If I move that +1 over, I get b is 1. And so my equation of that line is -x plus 1. Did that match up with a equals -1 and b equals 1 as another method? How do you like to look at a question? If I didn't draw the graph, I might not have thought of this method. But drawing the graph is like, ooh, it has to have those 2 points. And if I know 2 points, I can find the equation of the line. If I was just doing it algebraically, I would look at it this way and solve my system of equations. So that's the nice thing. As we get into more complicated math, you could solve things in different ways. But they're all based on, well, what has to happen, and what does that mean? What do I get from that? Algebraically, this is what came up, systems of equations. Graphically, I'm like, ooh, it has to be a line. I know 2 points on the line. This is what it would have to be. Here's our graph with Desmos. Once we plug it in, you see that it's nicely connected. And the next little part won't take us very long, and then I'll give you, we'll probably have about 10 minutes left where you can work on your next take-home quiz, or finish up the one that was due today. Different kinds of discontinuities. I like these names. If you were walking along this graph, and at -4, you had to go from this point way down to here, you'd have to jump. So we call this a jump discontinuity, where you can't just go from one side to the other really nicely. There's no quick fix for this. You can't make a straight line in between because then it doesn't stay a function anymore. So we call these jump discontinuities when the value from the left side and the limit from the right side are completely different numbers. So the jump discontinuities in this one happen at -4 and at 2. Sometimes, no matter how good you are at long jump, you can't jump from one to the other. Those are infinite discontinuities. They're kind of like a jump, but the jump is an infinite distance long. And so it's really hard no matter how much you practice. So in our rational function here, at x equals 3, we would say this is an infinite discontinuity. Because one side goes down to -infinity, the other side goes up to positive infinity. Technically, if they both went to positive infinity, we would still call it an infinite discontinuity, because there's not a certain jump you could do. And whenever your graph has a hole in it, we call those removable discontinuities. Because if you just took your pen and filled it in, it would be continuous. So you could remove it by adding a condition. I'm just plugging in that point, then all of a sudden it's continuous. So we call those removable discontinuities because if you define that point to be at that hole, then it would be continuous. So this one has a hole, but if you filled it in, it would be continuous. So these are removable discontinuities. You can do a lot with graphs that have removable discontinuities. The jumps are a little problematic. You can't make them continuous. Infinite ones you can't make continuous. But the removable ones, if you just colored it in, you would make it continuous at that point. So those are the 3 different types of discontinuities that we can have. And that's where we'll end for today.